Well, I'd like to welcome you all to April 2025 Science, Scripture, and Reason on behalf of our leadership team. I'm Randy Anderson, and we have the privilege of having Dr. Ken Wolgemuth with us this evening from Tulsa, Oklahoma. So we really appreciate you coming out, Ken, on Zoom to speak with us. Ken founded Solid Rock Lectures to communicate the wonder of God's handiwork in geology. He has a BS in chemistry from Wheaton College, a PhD in geochemistry from Columbia University, and a 40-year career in the petroleum industry. Ken was drawn into Christian worldview apologetics about 2 decades ago and became a Colson Fellow in 2017. He's given numerous lectures about creation and co-authored a 2018 paper on radiocarbon dating published in ASA's Perspectives on Science and Christian Faith. He is a contributing author to the groundbreaking book written expressly for the church, The Grand Canyon, Monument to an Ancient Earth. Can Noah's Flood Explain the Grand Canyon? And tonight, Ken is here to speak to us about the fine-tuning of the earth, which is God's divine design of the earth for life. And he will actually start off in outer space, I understand, and then focus down on the earth, looking at the core, the mantle, the crust, the water cycle, and the atmosphere, which are unique for life to exist. And that's the reason we can have this meeting. So Ken, again, thank you for coming, and I'm going to turn it over to you.
Thank you very much. Before I go ahead and make the slides at full scale, let me say just a little bit about my background. I grew up on the campus of Messiah College in Pennsylvania, where my dad was a professor there all of his career. So growing up in a church and a Christian family, I've known that God was my creator since I could talk. And we were got along really well. I got along very well with my parents, and Dad and I did a lot of outdoor things. And ultimately in the process, I followed him into chemistry, actually. So I learned right there in my first years of chemistry that the whole process of science is studying with some lens what nature is like, how did God put this earth together, and then what can we learn about God in that process. So that's some of the things I'll be focusing on here. It was because I was at Messiah College and then transferred to Wheaton that gave me the privilege of going to Columbia University, because Columbia was a recipient of a whole succession of Christian scientists there into the geochemistry program at Columbia University. And I just realized that both of my professors there had come from Wheaton when I got to Columbia. And in the windows of time that I was there in the laboratory, there were also 2 Christian brothers. So I wasn't there alone in that regard. And the science community, the geological science community, is not an environment where there's pushback about religion and Christianity. So that was kind of not an issue anyway, but we certainly hear of so many universities these days where there is strong pushback in certain fields. So having said that, briefly as an introduction, let me get my PowerPoint up to full scale yet. There we go. In my devotions this morning, I was reading this title that what I had given it, The Fine-Tuning of the Earth and God's Divine Design of the Earth for Life. And what caught my attention in putting that word divine in is that so often, as you well know, we do have an intelligent design community now based out of the Discovery Institute. And yes, it is intelligent design, but I think it goes just so far beyond our intelligence that when I learned from somebody else it would be good to use the word divine, I've started doing that pretty consistently now because indeed the design is so intricate and fabulous. A lot of my talks do center around the Grand Canyon, and as we exhibited at different meetings, our banner was like this, and we were there to tell creation's story, recognizing as Christian geologists and geochemists that the Earth, in fact, is ancient, and with that, we have a magnificent creator. Years ago, somebody showed me this picture of a volcano popping out smoke, and it comes from Psalm 104:32. He touches the mountains and they smoke, and that captured my imagination. This one is on the southern end of the Kamchatka Peninsula in eastern Russia. And then we find that God invites us to study his creation with this invitation, or speak to the earth and it will teach you, or let the fish of the sea inform you, from Job 12:8. So as followers of Christ and children of the Creator, God the Creator, he invites us to look at his creation. Here are two passages that I will show. He is the image of the invisible God. Of course, this is referring to Jesus Christ, the firstborn of all creation. For by him all things were created in heaven and on earth, visible and invisible, whether thrones or dominions or rulers or authorities, all things were created through him and for him. And the second passage here that I'm showing is Hebrews 1:2. But in these last days, he has spoken to us by his Son, whom he appointed the heir of all things, through whom also he created the world. So Jesus Christ is brought center in these two passages and a few others, that he is the creator. I've so appreciated what Johannes Kepler wrote during his time of looking at astronomy. The chief aim of all investigations of the external world should be to discover the rational order and harmony which has been imposed on it by God. There are naturalists, there are professors and professionals who are naturalists that have really recognized that this Earth is unique. Here's one published in 2000 by Peter Ward and Donald Brownlee. Plain up called it Rare Earth, Why Complex Life is Uncommon in the Universe. And then a second one in 2011, That We Are Alone in the Universe, Why Our Planet is Unique, by John Gribben. Within the Christian community, Guillermo Gonzalez and Jay Richards published this book, The Privileged Planet, in 2004, and How Our Place in the Cosmos is Designed for Discovery. They have just released last year a 20th anniversary edition of this same book. So to get an update, you can look to 2024. Their significant points that they made is that the universe is extremely fine-tuned for the Earth for two purposes. One is for life, and the other one is for discovery. And the biggest thing about discovery is our position of our solar system in the galaxy, the position of the Earth in the galaxy, of our sun in the galaxy, gives us a black space at nighttime that we can look out into the universe. Hugh Ross's first significant book on this same idea, he entitled Improbable Planet, How the Earth Became Humanity's Home. I really enjoyed the way he labeled some of the chapters in there, in that how it became our home. And he talks about the construction materials that are made up of the Earth. We're in the right neighborhood of the solar system and the galaxy to look out into space. The foundation is the Earth that we live in. The air conditioning is, he has it designed such that our temperatures remain moderate. And this will be one of the bullet points that I will show little later in my talk. And he prepares the continents that are ready to be occupied by humans as humanity started after the creation of humanity. In the Improbable Planet, he demonstrates a couple of very dramatic things, such as God's divine nature from Romans 5:12. We have a magnetic field that protects us from life. And number two, we're fairly unique, or totally unique, in terms of plate tectonics, which helps to maintain the suitable conditions for life in terms of the atmosphere. So we're protected because of the magnetic field, and we have support for maintaining suitable conditions. The next book that Hugh Ross wrote on this subject, released just a couple of years ago in 2022, is Designed to the Core. And he has about 2/3 of the chapters are looking into the galaxies and that are there, and we're in the right kind of a location in galaxy in our own galaxy for discovery. And then he also has selected a number of topics that are in the later chapters directly related to the Earth. Dr. Ling is a professor here at Oral Roberts University in Tulsa. And one year I was giving a back-to-back talk after his for a class in that the professor that was running the class knows both this Dr. Lang and me, invited me in. And this is one of the comments that he made, as he's primarily into astronomy type issues. The old model was a steady state of the universe that had just always existed. But in fact, the science community, naturalists, and everybody came to realize that it really had a beginning, and that beginning became nicknamed, that beginning became nicknamed the Big Bang. And it was said in a frustration of someone that is a naturalist, and they just saw that something big happened at the time when the matter came into existence. I prefer it to call it a big flash, because it's not a bang in the sense that a bomb is chaotic in the way it, if you will, destroys things. In fact, the creation event was very highly ordered. So a Christian brother of mine nicknamed it the Big Flash, which I use. This is not popular. This is me and my friend here in Tulsa. Astronomy has learned that at the creation event, the material that was made initially was 80% hydrogen and 20% helium. And then it was learned by nuclear physics that carbon-14 has a very special resonance in its electron shells and in the nucleus, that in the production of elements, this carbon-12 is a sort of a special block for the higher elements to be created and be formed in events that I'm going to show here in a moment. So here is a table of the elements, and it's hydrogen and helium that are the significant ones at the time of creation, as astronomers have identified through their tools to be happening 13.8 billion years ago. Now, where do all the other atoms come from that are of the 92 that we have that are stable and that we have on the Earth? Well, this comes from nuclear burning in stars, and it comes for supernova explosions that are an incredibly intense time of blast of making many, many elements. Nuclear physicists have produced these elements in particle accelerators, so they have learned the tools of understanding the behavior of these atoms among each other and fusing small atoms and elements into larger ones. The tools that are being used or the processes they refer to are called hydrogen burning, helium burning, carbon burning, and then this explosive nucleosynthesis. Hence the big flash, which I think of as Genesis 1:1. The sun is, of course, basically a big furnace that is fusing hydrogen into helium, which generates all the energy that we have here in our solar system. For the much bigger, the higher elements, larger elements, a lot of the activity of synthesis of additional elements is happening in red giant stars, and astrophysicists have learned from what they know about this nucleosynthesis processes that a red giant star has layers in it like onion layers, and they're at different levels in there. The heavier elements are synthesized. The supernova events happen at a time when a massive star collapses from the core, and that process of the collapse causes an intense explosion of nuclear burning, and that blast of a wave ejects material out into space with the synthesis of all the rest of the heavy elements. What I learned from Hugh Ross is that if the periodic table that we have now would be so completely different if there were slightly less mass in our universe. If it were slightly less, there would still be hydrogen and helium. No nuclear synthesis would happen. Now, don't ask me about the physics. That's beyond my pay grade, but I'm intrigued to learn this of part of the fine tuning of the astronomy components of our solar system, of our universe. Nothing else would be there. And the expansion of the universe is governed by the mass density and the space energy density. And those are so completely fine-tuned that the one is defined as tuned to the point of 10 to the power of 60, and the space energy 10 to the power of 120. And as we all know, with our level of science and what exponents are, that's crazy specific. In fact, this is such an astonishing degree of fine-tuning that this comment comes from an atheist, Lawrence Krauss. This is the most extreme fine-tuning problem known to physics. Boom. Now, if the periodic table were slightly more massive, we wouldn't have any elements less than iron. So the hydrogen and helium, the carbon, the nitrogen, the oxygen, the potassium, the sodium, and everything else would have all been fused into heavier elements. So there's a feature of the incredible fine-tuning from astronomy. Now, the interior features of the sun are significant in that it appears that the sun would have no twin. Among the hundreds of billions of stars in our galaxy, there are none that seem to possess the specific features required for advanced life to exist, in that the sun maintains its luminosity with 5 times greater stability than any other known star that astronomers have been able to study. So our sun is unique in that regard. So God has exquisitely fine-tuned the universe. This is an atheist physicist the British gentleman. Scientists are slowly waking up to the inconvenient truth. The universe looks suspiciously like a fix. Another cosmologist, Fred Hoyle. A super intellect has monkeyed with the physics. And that super intellect is what I was referring to when I showed my slide. I put this into divine. And then my favorite is actually from Robert Jastrow, God and the Astronomers. And it's my favorite because while I was at Columbia University at a laboratory outside of Manhattan, New York City, Robert Jastrow, an astrophysicist, was at a NASA office right there in Manhattan. So I had the privilege of hearing Robert Jastrow a couple of times during my graduate school days when he was giving a lecture at his office location and at their hall. And little did I know that 50 years later, I would be commenting about Robert Jastrow as an astrophysicist and something that he wrote in his book, God and the Astronomers. Here's what he wrote at the end of the book after giving what they've learned about the fine-tuning of astronomy. At this moment, it seems as though science will never be able to raise the curtain on the mystery of creation. For the scientist who has lived his life in the power of reason, the story ends like a bad dream. He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries. And I read his book, and he just couldn't come to the point of admitting that God actually existed, but he really had a sense of that uniqueness, that a super intellect is behind it. When I read that passage, I, as a geologist, can't help but thinking of Devil's Tower, of them climbing the mountain of ignorance and climbing up on top of that and finding the theologians there. So this gives me a chance to transition from astronomy to geology. Indeed, God has designed this earth for life. And now I want to show you a variety of things from geology and geochemistry that is evidence of fine tuning. And I'll talk about 4 different components: the Earth's magnetic field, plate tectonics, water, and Earth's atmosphere. Before I jump into these, do you want to ask any questions about the astronomy that I might have somewhat of an answer, but more likely I'd have to appeal back to Hugh Ross at some point?
I could ask a question about that carbon-12 resonance. I know that it's outside your field, but what does it actually mean? That something to do with, because of that resonance, that something, what is that?
Yeah, okay. What I told Randy when we talked, and Jim when we talked, I said, if I know the answer, I'll give it. I said, if I don't know a clear answer but could find something, I will do that. So this is going to be one of those that I will take this opportunity. So then later in another day or so, or a couple of days, I'll dig into the meaning of what that is, and I'll get back at least to a geochemist level. I think it has to do with the nucleosynthesis process in the stars, but I want to dig into it. I just don't have it off the top of my head. So thank you for asking that. That'll get me, and maybe even find a way to have a slide in there to comment about that. So thanks.
And one other question, if I
Yep.
may.
That's fine.
You were talking about the mass density of 10 to the 60th power.
Yes.
Being that fine-tuned to that degree. Are
Yeah.
we talking then about the periodic table being different if it was off by that degree, or is that a more something else?
That's what I understand, Hugh, to write. Yep, that's exactly what it means. This
Okay.
is in a design to the core, and I'll go look at it a little bit more. But yeah,
Thank you.
the nature of the nucleosynthesis processes depend on the mass of the universe. That is, beyond what I can comprehend. And I'll try to find some things that can relate to my level of experience or knowledge of geochemistry, but I'm not sure if I'll be able to do so, but I will try.
Thank you.
Yep. Okay, let's go look at the Earth's magnetic field. In that case, I'm going to highlight more. I did mention hydrogen and helium before, but now I'm going to add to that significant elements for the magnetic field are iron, nickel, and then for the Earth itself, the heating of the Earth, there's the uranium, thorium, and potassium. And these elements are particularly significant in a couple of ways. The Earth is made up in such a way that it has currently a solid core, and it has a liquid outer core, and then it has most of the Earth is mantle, and then there's a thin crust on top that floats on top of the mantle. The significance of the magnetic field comes from the fact that there is a liquid outer core, and it is understood to be up at something like 4,400 degrees Celsius. Whew. Here are some of the components. The inner core is considered solid iron from indications of where the mass is distributed in terms of the nature of rotation of the Earth. The outer core has iron and nickel and sulfur significantly in that liquid. The mantle is rather plastic. That is, it is rock, but it's plastic mode. It's thick. It can be moved, but very slowly. Then the significance of the uranium-238 and the thorium-232 and potassium-40 is that they were a combination of the stardust that formed our planet as our solar system was forming from the consolidation of a large gas cloud, with a Earth here being the third planet out from the distance from the sun. Just having the right amount of these radioactive atoms that when they decay, they release heat. So they are an important component of heating of the mantle or heating of the core to the point that the core is liquid. And that's a fine-tuning component that we do have liquid. We're the only planet in the solar system that has a liquid core, has a magnetic field. How is it generated? Well, the understanding is that there are currents of liquid iron and nickel in that outer core, and then the convection and the Coriolis force generate an electric field. And as the electric currents move around, they generate the magnetic field. It is nicknamed the Earth's dynamo. And again, a solid inner core, currents moving in the liquid outer core trigger the magnetic field in the pattern of those black arrows. When we look at the Earth at a larger scale, or looking in on it, you can see the pattern of the magnetic field, and what it accomplishes that it deflects harmful solar radiation and galactic cosmic rays that would damage the DNA of all the biosphere that's here. So it's a protecting device. It protects the atmosphere also, and the water vapor from being stripped off by the solar wind that would otherwise bombard the Earth. And here's a diagram of exactly that. in that these blue magnetic field lines deflect the solar wind coming from the sun so they don't blast straight into the body of the earth and strip away the oxygen, and preventing the dangerous radiation from reaching the continents where humans and other animals would be, that would be destructive. The poles have kind of a hole down through the magnetic field, and it's down through those holes that we hear about a solar flare, that the sun just blasts off a lot of solar wind, and the elements that are from that, when they come down into that northern part or the southern part of the earth, we get the northern lights that are so dramatic. And similarly down in the southern part of the earth, that some would see, say, from the southern part of South America. So is the Earth unique in this regard? It is the only terrestrial planet that has a strong enough magnetic field to protect life from damaging radiation. So the answer there is yes. Do you have any questions about the magnetic field?
Actually, I do. Sorry.
That's fine.
So
This is the time to ask them.
okay, so you mentioned the U-238, the thorium. Is that come into play yet, or is that later?
No, I'm using the uranium-238 as, for instance, the Earth we know was hot by two mechanisms. One is the heating up from the gravitational attraction as so much matter got crammed into this planet. Okay, so that's one factor. Those about 100 years ago who would try to find and figure out and calculate potentially the age of the Earth were doing so because they had a model of the Earth that it was so hot in the interior, and they would seek to calculate how long it would take from the heat that was accumulated from the gravitational attraction to come out and dissipate for the whole Earth to be cooling down from its original state. And the physicist who did that calculation came up with a number that was some several millions of years, and I don't remember what the number was. But then as soon as they discovered radioactivity, they realized that at the time he made that calculation, we didn't even know about radioactivity. So we had no awareness that these radioactive atoms were continuing to decay in this early Earth, and they're still here, decaying, and that was releasing heat. So they didn't have a correct understanding of the quantity of heat that was in the interior of the Earth. So that's kind of the gist of the issue related to that some of the heating did, in fact, significant heating to give us the molten outer core has come from that 4.5 billion years of radioactive decay. Half of the uranium-238 that was in the stardust has decayed away because that's the half-life of uranium-238. And then,
so
yeah.
is it still in the core? Because you showed an iron core. I didn't see any uranium in the core. So
uranium, potassium-40 uranium, the radioactive atoms are traces. I'm not expressing all the things that would be there.
Okay, that makes sense.
Yeah, now that the degree to which in the differentiation, once the interior got liquid, I don't know what other elements there might be also still in the core in terms of the iron and the nickel. And of course, uranium is heavy. It's the heaviest element.
Mm-hmm.
So there would probably have been an accumulation of a significant amount of uranium during that process also. But then it decays away with its respective a 4.5 billion year half-life. Yeah.
So there would still be some in the core then.
I expect there is some in the core.
Mm-hmm. Okay.
And the Earth, we know that's for sure. You know,
Yeah.
we measure it up here, and we measure it all over the Earth's crust. And when we get lavas that come up from the mantle, we get the composition of the uranium composition of those volcanic rocks that come up from that. Yeah. Yeah.
Okay, thanks.
Yep. There would still be some potassium. The potassium half-life is 1.25 billion years. So that's decreased about, what, 3 total half-lives. So it's down to, you know, maybe 20% of what it originally was. Thorium-232, I can't remember. I think it's even much longer. I'll have to get that in my head, but I don't remember it right now.
Ken, may I ask you a question also?
Yeah.
And again, I'm sorry, we're going back into a little bit into outer space, but the sister rocky planets like Venus and Mars, presumably were formed within the same kind of milieu as the Earth, yet they don't have the magnetic field because they don't have the, they don't have the abundance of the radioactive elements or the heavier elements, and why is that?
It could be a combination. They don't have the element, but they certainly don't have a liquid core. So it's some combination of the elements that were there that made up the other planets. Well, Mercury is pretty small, so that's a size issue there. Venus does not have a magnetic field, so for wherever to whatever significance the radioactive atoms needed to be important for the amount of heat, potentially there may not have been as much of those heavy elements near Venus, but Venus also is so close to the sun compared to the Earth that it doesn't even have a clear atmosphere. So it's a combination of both. I would expect that the distribution of these heavy elements is not uniform in the gases as these inner planets were formed. There was probably some differences there. I would expect that. How well those would be known, I'm not sure. That is more of an astronomy type, cosmology type question.
Yeah, thank you. I wonder whether there's some element of with the moon formation, the planetary collision forming the moon, and maybe
that could be part of it.
Maybe having a more concentration of elements there too. I don't know that, but I'm just speculating.
That could be part of it. Okay, let's look some at plate tectonics. There we have the Hawaiian Islands and the Emperor Seamounts that are formed from a hot spot in the mantle. That hot spot in the mantle has been spewing up lava through a plume over about the last 80 million years, as we'll see in a moment. And consistently, the Pacific Ocean plate is moving to the northwest over the hot spot in the mantle, so that successively the Hawaiian Islands, the whole chain right up to this bend, and then the Emperor Seamounts going up to the Kamchatka Peninsula and the end of the Aleutian Islands. This whole process has happened over about 80 million years. What we can do with radiometric dating by potassium argon methods is that we can get, from the islands, we collect the igneous rocks, and we can get a radiometric dating age of those that are collected. For the Emperor Seamounts, oceanographic research vessels have a dredge that they lower down, and they can grab igneous rock from those seamounts and then get that back up and take it to laboratories to do radiometric dating in potassium argon. And this was one of the earliest clear applications that the U.S. Geological Survey did in their Menlo Park laboratory in doing these calculations of developing these tools of potassium argon. Now, notice that we then have an age and we have a distance. So with that over 3,700 miles of drifting of that tectonic plate over 80 million years, that plays out that the movement of that plate on average, averaged out from slight differences, is about 2.9 inches per year, or I tend to round it off. It's moving basically at about 3 inches a year. And there we have current measurements that we can observe today in seeing the movement. It's about 3 inches a year. And then because of the radiometric dating, we're confirming with a modern measurement something that we can also trace by the radiometric dating ages of these islands, that they are successively older and older and older in a rhythmic pattern. How do they move? And what is the driving force in the mantle that triggers plate tectonic movement? Well, it's significantly because I've shown you that there's the liquid outer core, and that heats up the mantle. And I said that the mantle type rock is somewhat plastic. So there are convection cells that have been established in the mantle. And in that process, then those convection cells are such that the plastic lava moves upward and outward and helps to carry continents apart. And the result of this liquid lava coming up in this diagram, the mid-Atlantic ridge, new ocean crust is being formed continuously, but slowly, as those continents move apart. This diagram of Pangea and this animation was put together by Professor Tanya Atwater at University of California, Santa Barbara. And it's one that I appreciate so much because it's so easy to see the continents as we know them today. And I'll play this to show the example of the breakup of Pangea. And you can see North Atlantic opened first, now the South Atlantic, and now watch India crash into Asia. It isn't uncommon to hear somebody from Answers in Genesis say, well, there are marine rocks up on top of Mount Everest, so Noah's flood must have been up there at that time. And I come and I show this example where India has crashed into Asia, and it's India crashing into Asia that has formed the Himalaya mountains that has carried marine sediments and marine fossils high onto the Himalaya mountains. And here's the way I describe that in a diagram, and that 50 million years ago, that India subcontinent was still far to the south, and there was oceanic crust in front of it. And on the south edge of the Asia, there were marine environments of the growth of corals and marine animals that live with corals. And as India came closer and closer and then crashed into Asia, it has carried these marine sediments high indeed up onto the high reaches of the Himalaya mountains. And there is back up, hit too many. There's an example then of some of the layering that you can see of sedimentary rocks that are high up on the Himalayas. I showed this one time to a seminary student, and when I showed India crashing into Asia, her jaw just dropped. She said, "Oh, is that how those fossils got up there?" That was out on Mount Everest. That was out at Multnomah Seminary in California, and her response was worth the whole trip to me to be able to show that. The separation of North America from Africa on average over about 100 million years is about 1 inch per year. So here on this side of the continent, it's been about 1 inch a year. in the Pacific, it's going a little bit more. And you notice India moved fairly quickly up across the Indian Ocean area. And geophysicists have estimated that India may have had a little spike, that somehow down in the mantle, there was a period of more rapid driving India, maybe up to 5 or 6 inches per year for some window of time, not the whole time, but of course, once it hit India, then it slowed down. And in fact, that activity is still going on, because we hear of all the earthquakes that happen in the Himalaya mountains in Nepal, and Mount Everest is still rising a little bit at about 2 or 3 inches a year. Okay, now let's look at, let's see, plate tectonics. Let's look at life in the oceans. Well, the life there requires carbon, calcium, sulfur, phosphorus, etc. And during the growth of plankton and coral reefs, these elements are being removed from the oceans on a regular basis, and they get locked up in the sediments that are hence depleting the ocean of those elements. And here's a schematic of that part in terms of the activity of all the plankton and that are carrying those down into the sediments. The sediments get carried by plate tectonics and get driven in under, say, the Andes Mountains, if you're thinking about the Pacific Ocean Basin. Those lift up the mountains, and then the processes of weathering, erosion, rivers that flow carry elements back into the ocean. So it's a cycle, geochemical cycle of sodium and potassium and chlorine and the other elements that make up these minerals. There's so much tectonic recycling of these crusts that Michael Denton says this: a paradox is resolved that the tectonic recycling of the oceanic and continental crusts holds the key. This replenishes the ocean with the continental runoff by the reaction of water with upwelling magma at the mid-ocean ridges. So he's putting the puzzle together of the delivery and the recycling of these nutrients by plate tectonics. So plate tectonics promotes the biological productivity in the oceans, helps to increase diversity as a hedge against mass extinction, helps to maintain equitable temperatures that are necessary, required for animal life, which we'll come back to here after a little bit. And in that one book that I showed the cover before of the rare earth by some naturalists, it may be that plate tectonics is the central requirement for life on a planet, and that it is necessary for keeping the world supplied with water. Well, is the Earth unique in terms of plate tectonics? Yes, we're the only one that has that process. Any questions there on plate tectonics? Okay, let's look at water. There are 4 requirements that the planet needs in terms of having this liquid water. Number 1, the Earth has captured enough for it to be dominant in our oceans. Water that was accumulated early on has migrated from the interior up to the surface, and it's in our oceans. Here's a big one. Water is not lost to space. This is significant, as we'll see in a few moments here. And of course, the uniqueness of water, we all know in that it exists here predominantly as a liquid, but in the water cycle, you know, it evaporates and falls as rain and snow. So it's very significant in that regard. These pieces come from Wallace Broecker in a little book called How to Build a Habitable Planet, and also some of the content from that book, The Rare Earth. Now, as the Lord took me to Columbia University, I was able to actually do my thesis under this individual, Wallace Broecker, and he is known across the profession as Wally Broecker, and that's what he always went by, so I will call him Wally Broecker. And he wrote this book that, and one of the times I was giving a class somewhere, they had used this book in one of the courses that he took in college, that at whatever university that individual was going to. Wally Broecker sent me out on this research vessel after my first year at school at Columbia, which was a fabulous experience because I had an itch to go out on the ocean for whatever reason. The laboratory there is Lamont Doherty Geological Observatory, and over its 7 or 8 decades of existence, it has operated 4 different research vessels and logged 3.5 million nautical miles of their research. And the one step that I was on that ship was I'm just after my first year of graduate school at Columbia, and he put me on this ship in Victoria, British Columbia. We're sailing down here, and that is a port of call of Tahiti. And here I am, a kid from central Pennsylvania up in there, and thinking, oh my gracious, I'm 21 years old and I'm down here in the South Pacific. So I really did enjoy that step. And then the next step of the leg, we went through the Panama Canal, and then I got permission and I stayed on the ship until we got back up to New York at the end of that. Well, here's what he says about water. The Earth has about 0.5% weight water. The factors that lead to this particular capture efficiency are not too well understood. Our planet would have not been expected to have any water, but somehow it just got about the right amount to support life. So that's been one of the riddles that geochemists have been wrestling with, that Wally has included in his book, just raising the question, how did all this happen? One of the potential solutions that was published by a team in 2020, that the origin of Earth's water is debated, concurring with Wally. The inner solar system was too warm to have retained water as ice. So our terrestrial water is thought to have been supplied by hydrated materials that originally formed in the outer solar system and somehow were migrated inward. And the certain kind of asteroid bodies that have a lot of water are one of those that come, the ones that have a lot of ice that are up in space. So is the Earth unique for water? Well, yeah, it sure does. It has not lost its water over time because it's stayed here. That magnetic field is protecting the solar blast from the sun from stripping it off. Unlike Mars and Venus, we have retained the water, and so it's here. So that's a yes on that one. Any questions right now, maybe on water? Let's press on with the atmosphere. In the atmosphere, we really have kind of a Goldilocks zone. The air pressure must be light enough that it allows for the evaporation of water, but it also has to be heavy enough so that asteroids that are coming in from space into our solar system or in our solar system has enough capacity to destroy the asteroids and burn them up before they come crashing down on the continents, which happens to most of them, virtually all of them. We need evaporation because it drives the water cycle. And we have this really thick atmosphere that destroys the asteroids that do blow up in the upper atmosphere. And very few actually end up coming down and smashing into the Earth. And of course, one of the most famous ones is the one that hit and created the Chicxulub crater in the Yucatan Peninsula of Mexico that is synchronized with the demise of the dinosaurs and them going extinct. So there's one that was so big that it did not get completely destroyed. Well, it's a Goldilocks in gravity. The gravity has to be strong enough that we prevents losing the oxygen and nitrogen, but it also has to be weak enough so that hydrogen can escape, or hydrogen would build up in the atmosphere. So there's a balance. Earth and Venus are massive enough to hold these lightest gases, but Moon and Mercury do not have enough density to hold the oxygen and the nitrogen. So that's one distinctive. Now, a little bit about the history of the atmosphere. Ooh, that was the wrong button. There we go. From the decay of uranium-238, we have been able to learn that the Earth is 4.6 billion years old. Volcanoes spewed out lots of gases over history. Hydrogen sulfide, methane, and up to 200 times the concentration of carbon dioxide that we have in the atmosphere today was part of the early atmosphere. And here's a summary of the estimated components. Nitrogen, lots of carbon dioxide, of course, water, a lot of hydrogen sulfide, a lot of methane, ammonia. The wrinkle was there was no free oxygen. So for oxygen taking organisms, those could not get started early on. It's estimated that tectonic plates got going significantly about 2.5 billion years ago. 2.7 billion years ago, there's evidence that cyanobacteria were beginning to make some free oxygen from that photosynthetic type processes from carbon dioxide and the water. So bacteria were beginning to grow and produce some free hydrogen. Eventually, that became significant enough that there was significant photosynthesis. So this band of blue shows no oxygen and then slowly build up of oxygen. And then at about the beginning of the Paleozoic, which is the Cambrian explosion time window, oxygen in the atmosphere built up toward 20%, and which is approximately what we have today. This is the step that made it possible for cyanobacteria and for multi-celled animals to grow when they had adequate supplies of oxygen from the photosynthetic processes. So, composition of our atmosphere. Oxygen's high enough to sustain biological respiration, which we need and all mammals need. But it's low enough, less than 25%, to prevent it to be explosive or be even toxic to life. I've read this at least here from a fellow scientist that helped me with some of this content material that I'll mention a little bit later, and that wet organic matter apparently would burn freely if the oxygen were up to 25%. That's a killer for everything. It sits now at about 21%, just at a sweet spot between the dangerously high and the dangerously low. So composition wise, nitrogen is 78, oxygen 22, argon's about 0.9%, and all the others less than 0.1%. Nitrogen is incredibly unique with critical properties that make this feasible. Has the right density. It's not a greenhouse gas, so it doesn't capture the solar infrared radiation going back to the space. It absorbs ultra-low ultraviolet. It is not toxic to life. It's not flammable. It's hard to liquefy. It's transparent to UV, visible, and near infrared radiation. It's not reactive. It doesn't acidify water. It has a very low solubility in water. Yet it's necessary for life. So it's usable for a small amount is necessary for life. And these components of the atmospheric content come from Professor Ryan Hayes, and I'm using them with his permission. Now, the combination of the atmosphere makes the plate tectonics and the atmosphere kind of like a global thermostat. If it gets too hot, there will be more rain, there'll be weathering. That will be carbon dioxide is removed from the atmosphere and the earth cools. If it gets too cool, there's less rain, there's less weathering, carbon dioxide builds up in the atmosphere and the earth's warm. Hence, nickname a global thermostat. So here's a summary statement. A fabulous convergence among the plate tectonics, carbon cycling, liquid water in large amounts, atmosphere with carbon dioxide and greenhouse gases yield this global thermostat. So is it unique? Bingo, we have a strong magnetic field. We've got plate tectonics. We have large amounts of water. We have just a perfect night atmosphere for supporting life that serves as a global atmosphere thermostat. And 25 years ago, I thought there were probably many Earths in the universe with the gazillions of stars that are out there. But now in this 20 years of being very active in this faith and science community, I just marvel at how unique I'm learning that the Earth is. The Earth has been blessed with incredible good fortune, giving it all the right properties to sustain complex, beautiful biosphere. Earth is a very strange place, perhaps the luckiest place on the planet in the visible universe. And this comes from why Earth is exceptional. David Waltham. So I think of it, indeed, God is the divine designer. He prepared the earth for life. And I've shown you examples the way I see that it is fine-tuned and unique. And another person I need to thank is Casey Luskin with the Discovery Institute in Washington and Seattle, and particularly his components here about the water and the atmosphere. I give thanks to Casey. Friend of mine who is a believer, worked for Exxon for many years, lives there in Houston still. Hugh Ross points out that long-lived plate tectonics was absolutely essential for the Earth to have advanced life. The Earth could easily have been just another dead planet. If the plates oriented in many ways or were missing, there would have been a snowball Earth or a toasted Earth. No life, no continents such as we have, no continents, no advanced life. Such coincidences are entirely consistent with God preparing earth for beings that he would one day have a relationship with. I find them incredibly fortuitous for an accidental planet in an accidental universe that accidentally developed intelligent life. So Steve and I, as two Christian brothers in the oil field profession for our careers, feel exactly like this and blessed to be able to be studying his creation in this way. A very good book for the lay person who is not super science oriented comes from Michael Strauss. He's a professor over at University of Oklahoma. Does science conflict with biblical Christianity? He himself is a physicist who studies the Big Bang and the Bible with that collider that is over in Switzerland. It is so clear that the scientific community has overwhelmingly accepted the creation event, the Big Bang, which I, of course, sort of nicknamed the Big Flash. Thank you very much for your kind attention. We'll have some time for questions and go after it. Thank you.